Hello students, I Dr. Monika Tyagi, Associate Professor, Department of Applied Science and Humanities, IIMT College of Engineering, Greater Noida. Today, I am going to deliver a lecture on molecular orbital theory and its application on homo and heterodiatomic molecules. Before I start with molecular orbital theory, I give a brief account of atomic orbitals, atomic subcell, and valence bond theory. Heisenberg's uncertainty principle states that it is impossible to define what time and where an electron is and where is it going next. This makes it impossible to know exactly where an electron is traveling in an atom. Since it is impossible to know where an electron is at a certain time, a series of calculations are used to approximate the volume and time in which the electron can be located. These regions are called atomic orbitals. These are also known as the quantum state of the electrons. Only two electrons can occupy one orbital and they must have different spin states. Orbitals are grouped into subcells. This field of study is called quantum mechanics. There are some examples of atomic orbitals as subcell. There is one s orbital in n subcell. The electrons can be located anywhere within the sphere center at the atom's nucleus, and it is spherical in shape. P orbitals. It's shaped like two balloons tied together. There are three orbitals in a p subcell that are presented as px, py, and pz orbitals. These are higher in energy than the corresponding s orbitals. D orbitals. The D subcell is divided into 5 orbitals: dxy, dxz, dyz, dz square, and dx square minus y square. These orbitals have a very complex shape and are higher in energy than the s and p orbitals. The nature of chemical bonds. Covalent bond forms when two atoms approach each other closely so that a singly occupied orbital on one atom overlaps a singly occupied orbital on the other atom as shown in figure. Two models to describe covalent bonding are valence bond theory and molecular orbital theory. Valence bond theory states that a molecule is made up of atoms. Electrons in atoms occupy atomic orbitals. Covalent bond is formed by the overlapping between the orbitals having unpaired electron with opposite spin. Extent of overlapping depends upon nature of orbitals and type of overlapping. More the area of overlapping between the orbitals, more will be the strength of bond form. Only valence orbitals are involved in bonding and the identity of orbitals remain unchanged after overlapping. Drawbacks of valence bond theory. Valence bond theory could not explain the magnetic behavior of oxygen. According to valence bond theory, oxygen molecule should be diamagnetic, but experimentally it is found to be paramagnetic. It could not explain the color and magnetic behavior of the compounds. Valence bond theory cannot explain the formation of odd electrons like H2+. It has failed to explain the formation of complexes. Molecular orbital theory. The goal of molecular orbital theory is to describe molecules in a similar way to how we describe atoms, that is, in terms of orbitals, orbital diagrams, and electronic configurations. The main points of molecular orbital theories are as it is developed by F1 and R.S. Malkin in 1932. The valence electrons are associated with all the nuclei in a molecule, that is, valence electron of any atom. They are not the electron of the atom with the bind of a molecule. They are electron of molecule. Atoms have atomic orbitals as well as molecules have molecular orbitals. In molecules, there is no orbital of atom. Atomic orbitals is represented by 1s, 2s, 2p. whereas molecular orbital is represented by sigma and pi. Monocentric atomic orbitals overlap and form polycentric molecular orbital as shown in figure. Number of atomic orbitals combined is equal to number of molecular orbitals formed as shown in figure when two atomic orbitals, that is 1s and 1s, combine and the formation of two molecular orbitals is take place. Combining atomic orbital must have same energy, nearly same energy and same shape. Formation of molecular orbitals. Two atomic orbitals combine to form, they give rise a bonding molecular orbital and an antibonding molecular orbital. Electrons present in bonding molecular orbital are lower in energy and provide stability. Electrons present in antibonding molecular orbital are higher in energy and give uncertainty. Linear combination of atomic orbital. Schrödinger explained orbital is the place where the probability of electron is most likely to be found. Electron is probably wave, which we call orbital. The formation of molecular orbital takes place according to LCAO principle, which states that psi equal to psi A plus minus psi B. Psi A and psi B are the wave function of atomic orbital A and B respectively. When psi A and psi B are of same sign, constructive interference will take place and form bonding molecular orbital, which is shown in figure. Bonding molecular orbitals have lower energy and higher probability in comparison that of individual atomic orbitals. When psi A and psi B are of different sign, destructive interference will take place and form anti-bonding molecular orbital, which is shown in figure. In anti-bonding molecular orbital, probability of electron decrease and they have higher energy. If the atomic orbitals participate but don't overlap, they are called non-bonding molecular orbital. These non-bonding molecular orbitals having energy and probability equal to individual atomic orbital. Formation of sigma bond. Sigma bond is formed by the axial overlapping or head-to-head overlapping when two atomic orbitals combined, as shown in figure. 1s and 1s orbital is combined. Two types of molecular orbital take place by the additive combination. Bonding molecular orbital take place, which is shown by sigma 1s. By the subtractive combination of 1s and 1s, anti-bonding molecular orbital take place, which is shown by sigma star 1s. In the same manner, 2pz and 2pz orbital combined and the formation of bonding molecular orbital take place by additive combination of 2pz and 2pz orbitals, and antibonding molecular orbital take place by the subtractive combination of 2pz and 2pz orbitals. Bonding molecular orbital is represented by sigma 2pz and antibonding molecular orbital is represented by sigma 2pz. Formation of pi bond. Formation of pi bond take place by the sidewise overlapping of px-px or py-py orbital. Pi bond is formed such a way that they are remain parallel to each other and perpendicular axis. By the additive combinations of 2px and 2px, bonding molecular orbital is formed, which is represented by pi 2px, and by the subtractive combination of 2px and 2px, anti-bonding molecular orbitals take place, which is represented as pi star 2px. Electronic configuration. According to the molecular orbital theory, the filling of orbital takes place according to alpha principle, Pauli exclusion principle, and Kunz principle. Above principle state that electrons are filled in increasing of energy level as shown in figure. So two electrons can have the same set of four quantum number as Pauli exclusion principle. Kunz state that pairing of electron does not take place until all the atomic or molecular orbitals are singly occupied as shown in figure. Electronic configuration of lighter molecules. Lighter molecules are the molecules which have 14 electrons or less than 14 electrons. And the electronic configuration are as sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, pi 2px is equal to pi 2py, sigma 2pz, pi star 2px is equal to pi star 2py, sigma star 2pz. Electronic configuration of heavier molecules. Heavier molecules are the molecules which have the electrons 15 or more than 15 electrons. And the electronic configuration are as sigma 1s, sigma star 1s, sigma 2s, sigma star 2s, sigma 2pz, pi 2px is equal to pi 2py, pi star 2px is equal to pi star 2py, sigma star 2pz. Molecular orbital diagram. There are two examples of molecular orbital diagram. One is homonuclear diatomic molecule and other is heteronuclear diatomic molecule. A symmetrical molecular orbital diagram is formed when both the atomic orbitals have same energy level as shown in homonuclear diatomic molecule. In heteronuclear diatomic molecule, in this case, B atom is more electronegative than A. That's why bonding orbital is near B. Bond order. Bond order is equal to number of electrons in bonding molecular orbitals minus number of electrons in antibonding molecular orbitals. Bond order is proportional to stability, strength, dissociation energy. Bond order is inversely proportional to 1 upon bond length, 1 upon bond energy, and 1 upon reactivity. Magnetic behavior. If number of unpaired electrons are present in molecules, it shows paramagnetic nature, and all the nucleons are paired, then it shows dimagnetic nature. And the examples are given in figure also. Example of homodiatomic molecules. First example is hydrogen. Electronic configuration of hydrogen atom is 1s1. So, one electron is filled in both 1s atomic orbital of hydrogen atom. By the combination of 1s and 1s atomic orbital of hydrogen atom, two molecular orbitals sigma 1s and sigma star 1s is formed. Both two electrons are filled in sigma 1s. Electronic configuration of hydrogen atom is sigma 1s2. Bond order equal to number of electron in bonding, which is 2, number of electron in antibonding, which is 0, divided by 2 is equal to A. And all the electrons are fully filled, show the dimagnetic nature. The other example of homodiatomic molecule is nitrogen. The electronic configuration of nitrogen is 1s2, 2s2, 2p3. So electron is first going to be filled in 1s atomic orbitals of nitrogen atom. In the combination of 1s and 1s atomic orbitals of nitrogen atom, the formation of sigma 1s and sigma star 1s molecular orbital is formed. Now electron is going to be filled in sigma 1s, sigma star 1s. In the same manner, 2s orbital is going to be filled. by the combination of 2s and 2s atomic orbital, sigma 2s and sigma star 2s molecular orbitals form. Now electron is going to be filled in sigma 2s. Now sigma star 2s. Nitrogen contains 3 electrons in p orbital, in 2px, 2py, 2pz. In the same manner, the electron is filled in another atom of nitrogen. Now, the electron is going to be filled in pi to px and pi to py. The energy level of pi to px and pi to py is same. So, first electron is singly occupied. Now, pairing is going to be start. Now, electron is going to be filled in sigma to pz. All the electrons are filled in molecular orbitals. So, electronic configuration of nitrogen molecule is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi to px2 equal to pi to py2, sigma to pz2. The bond order of nitrogen molecule is 3. Number of electrons in bonding is 10 and number of electrons in antibonding is 4. All the electrons are fully filled, so show dimagnetic in nature. The other example of homodiatomic molecule is oxygen. The electronic configuration of oxygen is 1s2, 2s2, 2p4. Now electron is going to be filled in 1s atomic orbital of oxygen. In the formation of 1s and 1s atomic orbitals oxygen atom, the formation of sigma 1s and sigma star 1s molecular orbital is formed. Now electron is going to be filled in sigma 1s, now sigma star 1s, which is higher in energy. In the same manner, electrons is going to be filled in 2s. Now sigma 2s, sigma star 2s. In p orbitals of oxygen, it contains 4 electrons. Now electrons first is singly occupied, 2px, 2py, 2pz. Now pairing is going to be start in the same manner, 2px, 2py, 2pz. Now pairing is going to be start. Now electron is going to be filling sigma 2pz. Now pi 2px and pi 2py have the same energy. So first electron is occupied singly. Now pairing is going to be start. Remaining 2 electrons is going to be filled in pi to px and pi to py. The electronic configuration of oxygen molecule is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi to px2 equal to pi to py2, pi star 2px1 equal to pi star 2py1. Bond order of oxygen molecule is 2. As the diagram shows, it contains 10 electron in bonding molecular orbital and 6 electron in antibonding molecular orbital. In the last orbital, which is pi to px and pi to py, it contains 2 unpaired electrons, so its nature is paramagnetic. Coming to some example of heterodiatomic molecule. First example I have taken is nitric oxide. When nitrogen and oxygen, they are going to combine. The nitrogen has total of 7 electrons and oxygen has 8 electrons. When these are going to combine, a total of 15 electrons will be there. In this case, when we compare the electronegativity of oxygen and nitrogen, obviously oxygen is more electronegative than nitrogen. Therefore, atomic orbital of oxygen is lower as compared to atomic orbital of nitrogen. 1s and 1s of nitrogen and oxygen combine, the formation of sigma 1s and sigma star 1s take place. Now electron is going to be filled in 1s and 1s atomic orbitals of nitrogen and oxygen. In atomic orbitals of oxygen, Now electron is going to be filled in sigma 1s, which is lower in energy and more stable. Now electron is going to be filled in sigma star 1s, which is higher in energy. In the same manner, electron is going to be filled in 2s of oxygen. Now electron is going to be filled in sigma 2s, sigma star 2s. Oxygen contains 4 electrons in p orbitals and nitrogen contains 3 electrons in p orbitals. Now we are going to fill in atomic orbitals of nitrogen, 2px, 2py, 2pz. Now atomic orbitals of oxygen of 2p is going to be filled, 2px, first singly occupied, 2py, 2pz. Now pairing is going to be start. Now electron is going to be filled in sigma 2pz. Pi 2px and pi 2py have same energy level. So first electron is singly occupied. Now pairing is going to be start. Remaining one electron is going to be filled in pi star 2px. Electronic configuration of nitric oxide is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, sigma 2pz2, pi 2 px2 equal to pi 2 py2, pi star 2px1 equal to pi star 2py. This orbital is empty. Bond order of nitric oxide is 5. As shown in figure, in antibonding, the total electron is 5. And in bonding molecular orbital, the electron is 10. In the last orbital, which is sigma, in pi star 2px orbital, it contained 1 electron. So, it is unpaired. It shows paramagnetic in nature due to the 1 unpaired electron in pi star 2px orbital. The other example of heterodiatomic molecule is hydrogen fluoride. Hydrogen, the electronic configuration is 1s1 and the fluorine electronic configuration is 1s2, 2s2, 2p5. Since hydrogen has only 1 electron, this electron is high in energy and fluorine has total of 9 electrons and it contain only 1 electron which is unpaired. So the hydrogen high energy electron, it does not interact or it does not form bond with 1s and 2s of fluorine because of high energy difference. Therefore, bond formation cannot take place. So this 2p of fluorine is comparable in energy to the 1s of hydrogen, and in this case 1s of hydrogen combined with 2p Z of fluorine, resulting in the formation of sigma sp-Z and sigma star sp-Z orbital. So, this case 2px and 2py, since they are fully filled, they stay in non-bonding state and 2 electrons are filled in sigma sp-Z orbital. Now, electron is going to be filled in atomic orbital of hydrogen. It contains 1 electron. Now, electron is going to be filled in atomic orbitals of fluorine in 1s, 2 electrons are going to be filled in 2s, 2 electron. P orbitals contain 5 electrons. So, first they are singly occupied, 2px, 2py, 2pz. Now, pairing is going to be start. The combination of 1s and 2pz will take place sigma sp and sigma star sp molecular orbital. Now electron is going to be filled in sigma sp, 1s atomic orbitals of fluorine which is non-bonding, 2s, 2px, 2py the same energy for singly occupied. Now pairing, these are the non-bonding molecular orbitals. The electronic configuration of hydrogen fluoride 1s2, 2s2, sigma sp2, 2px2 equal to 2py2. The bond order of hydrogen fluoride is 1 as number of electron A bonding is 2 and number of electron is anti-bonding is 0 as the sigma star sp orbital is empty. All the electrons are fully filled, so it shows diamagnetic in nature. I've taken some problem related to the topic on the basis of molecular orbital theory explained by hydrogen exit as a diatomic molecule where as helium as monatomic form. As shown in the diagram of hydrogen molecule, it contains 2 electrons in bonding molecular orbitals and antibonding molecular orbital is empty. So bond order of hydrogen molecule is 1 and all the electrons are fully filled. So it shows diamagnetic in nature. In the figure of helium molecule, it shows 2 electrons in bonding and 2 electrons in antibonding. So bond order of helium molecule is 0. Due to the 0 bond order, molecule will not exit. The other problem related to the topic is arrange the following in increasing order of bond length N2, N2 plus, N2 minus. As shown in the figure, electronic configuration of nitrogen molecule is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px equal to pi 2p by 2, sigma 2pz2. And the bond order is 3 as the number of electrons is bonding is 10 and number of electrons in antibonding is 4. Electronic configuration of N2 minus is sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2 equal to pi 2p by 2, sigma 2pz2, pi star 2px1. As the number of electron in bonding is 10 and number of electron in antibonding is 5, so bond order of N2 minus is 2.5. Electronic configuration of N2 plus is 1s2, sigma 1s2, sigma star 1s2, sigma 2s2, sigma star 2s2, pi 2px2 equal to pi 2p by 2, sigma 2pz1. So bond order of N2 plus is 2.5, number of electron in bonding is 9 and number of electron in antibonding is 4. The bond order of N2 minus and N2 plus is 2.5, which is same. In this case, we will observe the electron in antibonding. In case of N2 minus, the number of electron in antibonding is 5 and number of electron in N2 plus is 4. As we know that number of electron increase in antibonding, the stability of molecule will be decreased. So in this case, N2 plus is more stable as comparatively to N2 minus because it contains less number of electron in antibonding as comparatively N2 minus. So increasing order of bond length is N2 minus, N2 plus, N2. Dear students, I hope this video will be beneficial to understand the basic concept of molecular orbital theory. With the help of molecular orbital diagram, you can type the electronic configuration of molecules, strength, stability, bond length, bond energy, reactivity of the molecules easily can be found out with the help of bond order. Thank you.